Hello everyone, today we're going to cover chemical thermodynamics for Unit 9. So chemical thermodynamics is a great lesson because we are going to talk about how thermodynamics gets affected using different lenses, using heat, and also how things actually work in terms of disorder. We'll be talking about the second and third law, first law of thermodynamics, and how everything connects back to some of the units we've covered. So let's go over to just a refresh of what thermodynamics was. So remember that at constant pressure, an enthalpy change occurs between the heat and the system and its surroundings. So think of, for example, this pan. The pan is taking in heat from the fire, and the fire is transferring that heat. And as that transfers and boils the water, we can calculate the heat being transferred using calorimetry experiments as an example. And remember that the amount of heat being transferred is the difference between your final initial H, which is enthalpy, with your initial, which gives us Q. That's how much heat was getting transferred to the pan. And Q represents that heat transfer. In thermodynamics, we usually talk about things like enthalpy changes, but also we talk about what we call order and disorder. So that's going to be a new topic that is going to be introduced in this unit. And I want you to really think about what happens when things get disordered or ordered. And so we're going to define this idea called spontaneous process or thermodynamically favored. So there's two terms here you want to think about. A spontaneous process, one that occurs without outside intervention. Now, this is a little misleading. Sometimes it doesn't mean it's going to spontaneously occur by itself. You need some sort of spark or activation energy. But generally what this means is that it's going to require, let's just say, minimal amounts. It's also called thermodynamically favored. And in the first law of thermodynamics, we talk about that energy is conserved. So we're going to be studying this and taking this to see if something is spontaneous. Let's first analyze this equation. The change in energy is equal to heat plus work, where delta E represents a change in the internal energy and Q represents heat transferred. So this is basically very similar to what we've been doing in the past about this idea that energy is being transferred from one point to another. And work is going to be pretty much defined as the movement of something. So in other words, pushing a box using energy as an example. So if Q is blank, we're going to figure out, remember, as a review, whether it released heat or not. So if Q is negative, it's going to release heat. And we defined that in previous lessons. While if Q is positive, it's going to absorb heat. So think of something like that's an endothermic reaction. Now, W is a little tricky because W refers to work. In other words, this motion. So if W is negative, meaning that, for example, the box did not move, the system did work. Negative, meaning that it's a negative value. If the system is positive, the system had done work. So in other words, if we have a box and we're pushing on it, that's going to be a positive amount. These conventions are from the system's point of view, so we're always looking at it from a chemical reaction, or we're looking at it from that specific point. Okay, so let's go over to a reversible. So if you remember from equilibrium, a reversible process is something where you can undo and get what you started with. So some reactions are considered to be reversible. And both the system and the surroundings always go back to the original state. So if I give you something where I want you to reverse course and change the color from green to blue or blue to green, backwards and forwards, we're going to call this a reversible process. As an example, there's certain changes of states, and so I'll give you a couple examples like ice and water. And ice is a phase change where we kind of go back and forth between these. And if I ask you how to go back from water to ice, it's very easy. We're just going to add some heat to it. In this example, it could be a couple of joules of energy. And if I want to go back from water back to ice, I'm going to take away some of that energy. Now, a irreversible project is one where you started with requires more than just what we'll call an undo. And so what you have to do is to restore the original system, but something has changed in the surroundings. So a gas expanding into an evacuated space is a great example. when gas expands, like let's say in this piston, you're going to have a situation where the piston is going to change its space. So if I remove this piece of material and I push on this piston, what's going to happen is the gas is going to get compressed. In order to have it go back, I would have to somehow put back the block and allow this piston to reverse. And that's obviously an irreversible process. I would need to do something extra to do that. And usually this is a little more difficult because I would have to add more gas or I would have to pull the piston. So points of note. Number one, when a chemical system is in equilibrium, we can reversibly go between a reactant and a product. And again, this kind of goes back to equilibrium points. The second one, in a spontaneous reaction or one in which it's thermodynamically favored, the path between the reactants and the products is irreversible. In other words, it takes a lot of energy to get it back to its original form. And the third thing is thermodynamics refers to the direction of this reaction, not its speed. So we're not interested in how fast something is. We're interested in, is it going to be favored in one direction or the other? And finally, in general, exothermic processes are more likely to be what we call spontaneous or thermodynamically favored. So processes in which a system disorder increases tend to occur spontaneously. So let's go ahead and talk about this idea called entropy. So entropy is a term that is used to describe this idea called a disorder. And we're going to refer this as SF minus SI equals to delta S. So in this example, if I have plus S to give you, we say that it's more disordered than R. In other words, the products are more disordered than the reactants. If it's negative, the products are more ordered than the reactant. And usually a large entropy equals to a large number we'll call a microstate, which is very, very disordered. And we're going to define this as a picture of a messy room with a room that also is very clean, potentially, and cars that are oxidizing and rusting and degrading over time. This basically means we are having more disorder. A small entropy generally means there's less microstates and is less disordered. And let's switch the picture here. And this is a picture of a more disordered, more ordered, and more ordered cars. So how does entropy occur at the particle level? So we have three types of motion that we know from kinetic energy: vibrational, translational, and vibrational, rotational. And if we take a look at how each one works, if we assume that we spin and we turn or move, what we're going to have is more kinetic energy. In more kinetic energy, we have more what we'll call entropy. And generally, the more entropy we have, the more microstates that we have, which in turn will increase entropy as temperature increases. So this relationship is given because the molecules are moving very rapidly, especially in a gas. And if entropy is defined in phases, we know that gases have the most kinetic energy, which means their entropy is very high. So let's talk about a process. So melting, freezing, condensing, and boiling. So in freezing, what you would have is a negative entropy because they are forming more of like a solid, while melting generally means that they're going to be turning more to a liquid, which means that the entropy will increasing. In condensing, we're going backwards, so that's going to be lower entropy, while boiling would increase. So the second law of thermodynamics states that entropy of an isolated system that is not in equilibrium will increase over time. These were researched by these two scientists, and they went ahead and said that the entropy of a universe increases in any spontaneous process. In other words, the universe will constantly have some sort of process that will increase entropy. And energy is not conserved. It is constantly increasing. For isolated systems, this becomes zero. And for irreversible reactions, it's going to be greater than zero.